and the topic for today is network functions. Before we start the topic, I'd like to recall what we did in the last lecture. We first proved Thevenin's theorem, and to recall what Thevenin's theorem is, it is that if a network N which contains sources, current sources as well as voltage sources and elements, network elements, but no magnetic coupling between N, there are voltage sources N V, there are current sources M I, and if this is connected to a load Z L, then the current I L in the load, as far as the load is concerned, the network behaves like a voltage source V T, which is equal to the open circuit voltage in series with an impedance Z T, then a Z L, and this current is I L. These two networks are perfectly equivalent to each other, provided Z L and N have no magnetic coupling. V T is the open circuit voltage and Z T is the impedance looking into the network N with current sources and voltage sources replaced by their internal impedances, but control sources being untouched. Control sources should be left as they are. This is Thevenin's theorem, and starting from Thevenin's theorem we can very easily derive Norton's theorem, and we did it a bit hurriedly in the last class. Now let us look at that. Look at this derivation of Thevenin's theorem, Norton's theorem. By Thevenin's you get I L equal to V T divided by Z T plus Z L, and we wrote this as V T by Z T multiplied by Z T by Z T plus Z L. This can be written as I N, if you call this as I N Z T by Z T plus Z L, and you call Z T as Z N, then the equivalent circuit becomes a source I N, then a parallel combination of Z N and Z L, which indeed is Norton's theorem. Norton's theorem says that as far as the load current is concerned, the network can be replaced by a current generator whose current I N is equal to V T by Z T, and if you look at this equivalent circuit, V T by Z T is the current obtained here when Z L is equal to 0, that is the short circuit current. So the current I N is the current flowing through a short circuit at the terminals of the network, and the parallel impedance Z N is the same as Thevenin impedance, Thevenin equivalent impedance, that is the impedance looking into the network after replacing the current sources and voltage sources, independent ones, by their internal impedances. I repeat this because people make mistakes. Independent sources have to be replaced by their internal impedances, but dependent sources should be left in peace. Okay? No disturbance to dependent sources. We want to take an example from the from the text to illustrate the application of Norton's theorem, and this example that I have chosen is 7.8. The example says that there is a 10 ampere current source. The problem is to be solved by Norton's theorem. While solving such problems, I continue giving you tips on several peripheral things which I would like you to pay attention to. For example, here I shall tell you something which is a trick of the trade, which if you remember, then you shall be able to analyze networks much quicker than others who do not remember. Okay? There is a current source which is switched off here at t equal to 0. So if the switch is on, all the current will pass like this. If the switch is off, the current will pass in the other direction, and in the other direction you have a 0.1 ohm in parallel with a 1 farad capacitor, then you have a 0.1 ohm resistor and a parallel combination of 1 farad capacitor and 0.1 ohm resistor. The voltage that is needed, the response that is needed is the voltage across this parallel combination. Okay. The and you have to solve this network by Norton's theorem, by application of Norton's theorem. So, this is the load as far as Norton's theorem is concerned, this is the load and this is the network. Okay. But first let us draw the equivalent circuit in the transform domain. It is given that the energy sources, that the capacitors are initially energy free, that means they are relaxed. In case they had initial conditions, then all you do is replace them by their equivalent circuits either in the time domain or in the transform domain. Well, we shall work in the transform domain, and initial conditions, if these capacitors are initial condition free, then the transform equivalent circuit is 10 by S, alright. This current source is 10 ut, so it becomes 10 by S. Then this combination 0.1 ohm and 1 farad can be combined into a single impedance, alright. Then we have a 0.1 ohm and again 1 farad and 0.1 ohm, they can be converted into a single impedance, and both of these impedances are, now this you should remember, that whenever there is a resistance and a capacitor in parallel R and C, the equivalent impedance is R multiplied by 1 by SC divided by R plus 1 by SC. And you should remember that on simplification this simply becomes R by SCR plus 1. This you should remember always, then you do not have to write this again and again. Okay. So, both of these impedances are 0.1 divided by SCR, so 0.1 S plus 1. Both of these impedances are equal to 0.1 divided by 0.1 S plus 1. Is that okay? This is something which you should remember throughout your life. Okay. Therefore, if I apply Norton's theorem, the current source ISC, you can easily see that this would be 10 by S multiplied by this current will split into two parts, one is through this and the other through 0.1 ohm, and this will be short circuited. Okay. So, this would be 0.1 divided by 0.1 S plus 1, the other impedance, divided by the sum of the two impedances, that is 0.1 plus 0.1 divided by 0.1 S plus 1, which you can now simplify. Okay. This is ISC. Now, to find out the ZT or Zn, is this okay? You can simplify this, you cross out 0.1 S plus 1, then you get 10 by S, 0.1 divided by, I can also cancel out 0.1, why not make it 1? Okay. Then I shall have 1 divided by 0.1 S plus 2. This will be the simple, which is very small. Oh, the writing is small. I thought the impedance was small. No. Okay. ISC would be equal to 10 by S, the 1 divided by 0.1 S plus 2. This is the current source, and the equivalent admittance, equivalent impedance is the same as Thevenin impedance, and that would be 0.1 divided by 0.1 S plus 1, this is the impedance, then in series with 0.1 ohm. Do you agree that this would be my ZT or Zn? Because in parallel with this there is a current source which is open circuited, and therefore ZT is equal to 0.1 plus 0.1 divided by 0.1 S plus 1, which you can see is 0.1 S plus 1, 0.1 S plus 2 multiplied by 0.1. Okay. So, we know ISC and we know ZT. Therefore, the voltage response V, if you go back to this circuit, well, my circuit is now this ISC in parallel with ZT in parallel with ZL, which again is 0.1 S divided by 0.1 S plus 1, and it is this voltage that I want to find out. So, capital V is simply ISC ZT parallel ZL, agreed, ZT parallel ZL, and you can now find out this expression and find out by inversion V of t, that is the time domain response. Okay. I would not I would not do the algebra, I will leave that to you. Agreed? So, we have shown an example, we shall work out other examples in the problem session for Norton's theorem, some very interesting examples. We now turn to the main problem, main topic of today, namely network functions. As I have said earlier, a network, in order to be useful, must have an excitation and must have a response, must have an excitation and must have a response. These are the three three essential components of circuit analysis or circuit synthesis. Okay. If I call the excitation as small e of t and its transform as small e of s, and the response is capital R of s, the transform of the response, then you know the network function f of s is the ratio of the response transform to the excitation transform. Okay. This is the network function, definition of network function under the condition that the network is initially relaxed. That must be remembered. A network function is defined only under that condition. The network is initially relaxed. Okay. This must not be lost sight of. Okay. Now, the network function f of s, as you know, could be, I have already told you this, could be a driving point function dp, driving point function, that is if the excitation and the response are at the same port or same pair of terminals, that is the excitation is either a voltage or current and the response is either a current or voltage. That is the only thing that you can do. So, the function f of s, network function f of s, can be either driving point, and if it is driving point, it could be either impedance or admittance, and the both of them are combined into a single term called immittance, and we call this DPI, driving point immittance function, or it could be a transfer function, that is if the excitation and response are at different ports, then it could be a transfer function, and the transfer function could be either an impedance or an admittance or dimensionless. Okay, it is a transfer impedance if the response is a voltage and the excitation is a current, all right, then it will be a transfer impedance. It will be a transfer admittance if the response is a current and the excitation is a voltage. It is dimensionless if the response and excitation are both voltages or both currents, and therefore dimensionless transfer function can again be split into two classes, that is voltage ratio or current ratio. These are matters of terminology. I have already explained earlier, I recall these various kinds of network functions, and then I take a simple example to illustrate what these mean. All right. Let us take this example. I have a current generator I. Now I am drawing the in terms of the transforms, and since I am talking of network function and therefore I am talking of initially relaxed elements, let us say I have R, L and C. Okay. Now obviously the driving point function, the driving point, you are driving only at this port, so the driving point function can be either an impedance or admittance. Instead of a current generator, if you had a voltage generator, then you would measure the current. So I by V would have been the driving point function. In any case, the impedance Z, the driving point impedance Z, driving point impedance. Why do you call driving point? Because there are other kinds of impedances. There can be a transfer impedance also. So the driving point impedance obviously is given by R plus. Now this also you should remember that whenever L and C are in parallel, then you get SL multiplied by 1 over SC divided by SL plus 1 over SC, and this is simply S squared LC plus 1. So I get SL divided by S squared LC plus 1. This is the driving point impedance. The driving point admittance Y is simply the reciprocal of Z. Okay. The driving point admittance is simply the reciprocal of Z. Now if I want to find out, let us say this voltage, if this voltage is your response, capital V, I beg your pardon, plus minus, then the transfer function would be a transfer impedance V by I, and the transfer impedance V by I, obviously if you look at the network, it shall be equal to parallel combination of L and C, which is SL by S squared LC plus 1 multiplied by I divided by I. Therefore this is the transfer impedance. Is that okay? V by I, capital I is a current generator, so R does not affect the current. This current flows through a parallel combination of L and C to produce a voltage capital V, and therefore V by I, the transfer impedance is simply SL by S squared LC plus 1. What would be the transfer admittance? Suppose it was a voltage generator. Suppose we had a voltage generator here, Vg let us say, and we had the same network R, L and C, and this current, let us say, this current was the response, alright. Then you see transfer admittance is IC divided by Vg would be equal to, yes, 1 by R plus SL divided by S squared LC plus 1, this gives the total current, then multiplied by SL divided by SL plus 1 over SC. Is that okay? I have found out, what I have found out is the total current first, that is this current is Vg divided by the total impedance, then this current splits into two parts, SL divided by SL plus 1 over SC. I can write this down by inspection. This is the transfer admittance, alright. Now let us go back to the equation, to the circuit, and see if we can define two transfer dimensionless transfer functions. First let this be the current ILC, and suppose this current is my response, then the current transfer ratio I sub C by I, which is a dimensionless transfer function, would have been simply SL divided by S squared LC plus 1. No, that is not correct. Is that okay now? You see the current flows and then splits into two parts. So it would be this current I sub C would be equal to I SL divided by SL plus 1 over SC. Is that okay now? Is the dimensionless current transfer function, Suppose I replace this by a voltage source now, let us say Vg, and I want to find out, this is my V, the dimensionless voltage transfer ratio, then obviously V by Vg would be equal to SL divided by S squared LC plus 1 divided by R plus SL divided by S squared LC plus 1. These finding such quantities in simple networks like this should be done by inspection. No loop equation, no node equation, no Thevenin's theorem, no Norton's theorem. It should be done simply by inspection. As long as you can do, that is the best thing to do. Observation, there is no replacement for a keen power of observation, and that is the strongest tool. Common sense and power of observation, these are the two strong tools for an engineer. Now let us go back to our response transform. R of S is equal to network function multiplied by excitation transform. This is the equation. Definition of network function is transform of the response divided by the transform of the excitation with the network initially relaxed. Okay. Now you see that if I take the inverse transform of this, okay, then there would be two types of terms. One would be the terms, the poles of f of s, and the other will be due to the poles of E of s. Okay. Is that clear? There will be two types of terms. For example, if S sub I are the natural frequencies of the network, then they will belong to f of s. They are properties of the network. And suppose the frequencies, forced frequencies are, let us say, S sub j, then obviously R of t would be summation of some a I e to the s I t over I plus summation b j e to the s j t over j. Is this point clear? No. All right, let us take an example. Yeah, correct, that is where I am coming to. Okay. Let us take an example. Suppose I switch on a battery to an RC network. This is my battery is, let us say, V sub G battery, and my response is the current I of t. Okay. So I know I of s would be equal to Vg by s, all right. This is the voltage transform divided by the impedance, that is 1 over R plus 1 over Sc. Agreed? We are assuming, of course, that the initial conditions are 0. Now this I can write as V sub G by S multiplied by Sc divided by Scr plus 1. Well, this is not a very good example, but let me make a modification. Instead of a battery, this is Vg, let us say e to the minus t, all right. Instead of a battery, it is an exponential source, Vg e to the minus t switched on at t equal to 0. This will bring out the point more clearly. What I have is then Vg by s plus 1. Agreed? The transform would be Vg by s plus 1. Therefore, the response transform I of s now consists of, okay, let me write this down again, Vg by s plus 1, then I write this as s plus 1 over Cr, C divided by Cr. Agree? So, C and C cancels, therefore, this is Vg by R, which is a constant, multiplied by 1 over S plus 1 multiplied by S divided by S plus 1 over Cr. Agreed? Now, you notice that the response transform has two kinds of terms besides this constant. Constant is simply a constant multiplier, so we can retain it as it is. It has two types of terms. There is a pole of the transform due to the excitation function. This pole is at S equal to minus 1. Agreed? There is a pole. The response blows up when S equal to minus 1, so it is a pole. The other term, S by S plus 1 by Cr, has a pole which is characteristic of the network. It does not arise because of the excitation, it arises because of the network, all right. And you know S equal to minus 1 by Cr is a natural frequency of the network, all right. And therefore, without making a partial fraction expansion, I can write I of t equal to, in terms of constants, I can write this as a1 e to the minus t because of this term plus a2 e to the minus t divided by Cr. Agree? So, there is a term due to the forcing function which was e to the minus t, and there is a term due to the natural response of the system. Again, it corroborates with the fact that the total solution shall be the sum of two functions. One is the complementary function and the other is the particular integral. The particular integral represents the forcing function natural frequencies. Okay? If this was a sin omega t, we would have got a sin omega t term here, whereas the complementary function is the solution to the homogeneous equation and represents the natural frequencies. To take another example, suppose we had, yes.
In this case, you are directly writing from IS to IT. So there is one S in the numerator of IS.
Oh, doesn't matter. If I make a partial fraction expansion, I will get a1 by S plus 1 plus a2 divided by S plus 1 over Cr.
S square.
In case we have S squared, then you shall have to write this. Okay, that is a good question. Suppose we have an S squared. Suppose my network function is S squared by S plus 1. Then what is the partial fraction expansion of this? Well, you will have to write as S plus 1 divided by A. Okay. So, you will have to divide numerator by denominator and take account of such terms. Now, what is the inverse transform of this? Delta prime t. The term transform of delta t is 1. Inverse the transform of delta prime t is equal to S.
So, but in this case, A is a function of S, isn't it?
Pardon me?
A is a function of S, it is not a constant.
A is equal to minus.
Again it comes.
So, this is not a correct solution. This is not a correct, I was waiting for this. This is not a correct partial fraction expansion. What should we do? We must have
A plus B.
a constant b. Okay? Then everything is taken care of. You see, we will have S square plus S plus A plus B S plus 1. Now we can cancel S and BS. S squared can remain, A and B. A plus B has to be equal to 1.
So does that imply that if in partial fraction, then in numerator if S comes, that won't be taken?
That won't be taken, why not?
That means, sir, suppose in any...
Here there is no problem, I tell you. Okay, let me illustrate one by one. One is that a network function shall always be a rational function. That is, it will be a ratio of a polynomial n of s divided by d of s. It will be a rational function. If the numerator degree is less than the denominator degree, then there is no problem. You can always write this as summation ai divided by s minus si. If the numerator degree is equal to the denominator degree, then you have to take out a constant. That is, you will have to write this as some k plus n1 s divided by d of s, where n1 is at least 1 degree lower than d. Hasn't this been taught in signals and systems in partial fraction expansion? It must have been. Alright, does not matter, we recall if n of s degree was higher than the degree of d of s, suppose n of s degree is 2 plus degree of d of s, then you have to take out a term like a1 s squared plus a2 s plus a0 plus n2 s divided by d of s, where n2 is at least 2 degrees lower than d, at least 2, it could be more, because not only the second degree term but another term may also cancel. Okay. So we will come to these applications. We are not going to discuss why it is so. We will come to these applications when we come to specific problems. Okay.
So what is the representation of differential of delta t in the time domain?
In the time domain, well, it's doubly infinitely large. You are differentiating a discontinuous function which is 0 at t equal to 0 minus, 0 at t equal to 0 plus, it exists at t equal to 0, the amplitude is infinity. So you are differentiating an infinite function and it is only a conceptual quantity, however its Laplace transform exists. Laplace transform is simply equal to s. In the time domain you can't also imagine a delta function, an impulse function. It is conceptual, alright. You cannot generate it in the laboratory. In the laboratory what you can generate is this, alright. And if you differentiate this, then you will get two delta functions, one here and one here, negative.
It should be 0, sir.
What should be 0?
Delta dash t.
Delta dash t is 0 for t equal to 0 plus, it is 0 at t equal to 0 minus, but at t equal to 0 it is not 0, it is infinitely large. Well, that is conceptual, you cannot generate this in the laboratory. But let me go back to the original premise, that is, I had shown that R of s is the product of network function and the excitation transform. So in R of t there will be two kinds of terms, one would be summation of terms like this where SI's are the natural frequencies, and the other would be summation of terms like this which are the reflections of forced frequencies. SJ's are the forced frequencies, they are poles of E of S. The qualification or the restriction on S sub i's, there is a restriction on S sub i's, and this restriction is that real part of S sub I, restriction, let me put it in red, there is a restriction on the natural frequencies. It says that real part of S sub I must be less than or equal to 0. The real part of S sub I must be less than or equal to 0. Now this can be supported by physical concepts like this, that S sub i's represent natural frequencies, and therefore the natural response or the complementary function shall contain terms like e to the sigma I plus j omega I multiplied by t, that is sigma I plus j omega I is Si, it is a real part and an imaginary part, that is e to the sigma I t e to the j omega I t. Now this is oscillatory, as you know, it contains sine and cosine, okay, cosine omega I t plus j sine omega I t. This is an exponential function, and if sigma I is allowed to be positive, then naturally the natural response shall grow in time indefinitely, or in other words the circuit will be unstable. Now a passive circuit cannot become unstable, that is, it cannot generate a current or voltage which grows indefinitely without limit, and therefore real part of S sub I, the natural frequencies, must be less than or equal to 0. If I consider the complex plane, that is the S plane, in which this is real part and this is imaginary part, then S sub I locations should be such that the real part is always non-negative, it can be 0. For example, if you have, let us say, a parallel combination of L and C, the natural frequencies are on the j omega axis plus minus j 1 by root L C. What is the product? What is the impedance? SL divided by S squared L C plus 1. So where are the poles? Poles are at plus minus j by square root L C. So you can have poles here on the j omega axis, alright, and it can be the real part of this is 0. The real part has to be either 0 or negative. In other words, the real part is not, I am sorry, the location is not allowed, the poles should not cross the j omega axis to the right. So the possible locations of natural frequencies is the left half of the S plane, left half of the S plane. Okay. Now the j omega axis, the imaginary axis, can be equally demanded or claimed by the right half and the left half. So how do you indicate that left half of the S plane including the j omega axis? Okay. You have to say the location of natural frequencies are left half of the S plane including the j omega axis. In mathematics there is a term for this. If the left half of the plane is to include the j omega axis, we call it a closed left half plane. Closed left half plane, that is, the boundary on this side is closed, j omega axis is not available to the right half plane. Is that okay? On the other hand, if we had strictly real part of Si, if it was strictly less than 0, then we would have said Si's lie in the open left half plane. Is that clear? Open and closed. A closed left half plane is left half S plane plus the j omega axis, and open one is left half of the S plane excluding the j omega axis. Okay. These terms we shall use later very frequently, open left half plane and closed left half plane. Now we will conclude this class with an example. I have 15 minutes more, and this example is 721. Please try to follow what I have been doing. It is a simple example, can be solved by inspection, and that is what we will do. We will not write in a loop node or even Thevenin's Nortons, we will not do that. This example is that there is a current source I of t, there is a capacitance C, there is a resistance R, and there is an inductance L. L is 1 Henry, that is given. This is the response that is to be found out, V of t. The circuit is initially relaxed. The question is, circuit is initially relaxed, the question is to find out the network function V of S by I of S. What kind of a function is this? This is a transfer impedance, voltage by current. So this is a transfer, we can write this as Z T of S, where this T, not Thevenin, this T stands for transfer. Okay. You have to find out this, and number 2, if ZT of S has poles of the transfer impedance are at the two locations shown. Here and here, this is -1 and this is -2. Poles of ZTS are given, one is at -1 and one is -2. You have to find out R and C. Okay, that is the second part of the question. First part is find this, then if the poles are located like this, what are the values of R and C, and the third part of the question is third part of the question is, if I of t has this waveform, this is 0 and this is 1, this is 5. If I of t has this waveform, that is, it is a window, it is a pulse, okay, or it is a gate, then if I of t is this, then what is V of t? These are the three parts of the question. Now to solve it, first thing first, we look at the circuit. I have capital I, C, R, L is given as 1 Henry, okay, and therefore capital V would be equal to I. Now I do by inspection, I first find the current in this and then the voltage, okay. The current would be 1 over SC divided by 1 over SC plus R plus S, L is 1 Henry. This is the current through this branch, this should be multiplied by S to get the voltage. So, is that point clear? Okay. So, the transfer function V by I would be equal to 1 over C. Now, let us look at it like this. Yes?
In the last part, aren't C parallel to series of R and L? Yes.
That is okay, but I have a current generator. So, what I am trying to find out is this current. Okay? It is not this voltage that we are required to find out. If that was so, if this was the voltage, then it is a driving point function. We would have simply found out the impedance of C in parallel to R and L. That is not what we want to find out. I want to find out this current, then multiply this by SL to get the voltage. Okay? The simplification is the question answered? The simplification would be, let us include L first and see what this is. Sorry. So, my V by I would be, I first multiply by SC, so I get I SL divided by S squared LC plus SCR plus 1. I won't be there, okay, fine. Then I write S, I want to write this as S squared plus, because I want to find the poles. So, the highest power term is made unity. Similarly, in the numerator, highest power term is made unity. So, L by LC, S squared plus S, R by L plus 1 over LC, that is equal to 1 over C S divided by S squared plus S R by L plus 1 over LC. It is given that the poles of the network function are at -1 and -2. So, this denominator polynomial must be S plus 1 multiplied by S plus 2. So, it must be S squared plus 3S plus 2, which means that capital R equal to 3 ohms and capital C would be how much? Half farad. So, you have found this out, okay, and therefore, my network function V by I becomes equal to 1 by C is 2. So, 2S divided by S squared plus 3S plus 2. This is my network function, and therefore, capital V would be equal to the network function multiplied by multiplied by capital I of S. Now if you had looked at capital I is simply this pulse, amplitude 5 and the times are 0 and 1. So what is capital I then? 5, in the time domain it will be 5 ut minus ut minus 1. So in the frequency domain it is 1 by S minus e to the minus S divided by S. That is because of ut minus 1, alright. Therefore my capital V simply becomes equal to this, which is equal to 10 times yes 1 minus e to the minus S, if I simplify, S squared plus 3S plus 2. Agreed? Is that okay? And inverse transform, with a little practice you should be able to write it down by inspection, because I know S squared plus 3S plus 2, I do not have to write and find the coefficients. I can write this directly as S plus 1 minus 1 by S plus 2. Is that okay? Alright. Therefore my V of t would be equal to 10 ut minus ut minus 2. I beg your pardon, this is not correct. Therefore my V of t would be 10 e to the minus t minus e to the minus 2t multiplied by ut, then minus, if it is multiplied by e to the minus S, that means t should be replaced by t minus 1. So it would be e to the minus t minus 1 minus e to the minus 2t minus 1 whole multiplied by u t minus 1, and this is written down by inspection. With a little bit of practice, an electrical engineer should be able to solve a circuit like he is throwing a dirt out of his fingers, okay? Just like it should be as easy as that. Okay. On the next occasion, that is on Thursday, I still have 2 minutes. This watch seems to be fast. Okay. On the next occasion, let me introduce the topic. We shall consider sinusoidal network functions. That is, what we have considered here is f of S, a function of the complex variable S. How does this function behave on the j omega axis? Now what does the j omega axis correspond to? It corresponds to sinusoidal excitation. Okay, as you know, e to the j omega t is cosine plus j sine omega t, so its real part as well as imaginary part is sinusoidal. Now given f of S, we can of course find how it behaves on the j omega axis. You simply put S equal to j omega. Okay, and we shall see that this function, which in general is a complex quantity, can be described by its amplitude and phase in one manner, or by its real part and imaginary part. The amplitude phase description is the Eulerian description, Euler, E-U-L-E-R, that is a polar description. Okay, amplitude and phase, that is we write some m omega multiplied by e to the j phi omega. On the other hand, the real part and imaginary part description is due to what kind of description can you call it? Cartesian. Okay, whose name is associated with Cartesian coordinates? Descartes, not Cartes. There is a D, D-C-A-R-T-E-S. We shall have occasion to look at these gentlemen, Euler, Descartes, Laplace, in this class on some near future date. We will know a little bit about them. Okay, it will be very fair. It will be very fair if you know when you are writing e to the j theta equal to cosine theta plus j sine theta. It's a very simple thing for you, but it's not a simple thing for Euler. Okay, So we'll do this sometime in future. Thank you.